Hey guys, Mr. Middleton here. Today we're going to talk about tangent lines. At the end of this video, you should be able to use the properties of tangent lines to find missing side lengths and angle measures. Okay, so a tangent line to a circle is a line that touches the circle in exactly one point. Okay, so if you see that here, adjust just a little bit so we're at the top of this. The point where the circle and the tangent line intersect is called the point of tangency. Point of tangency. Okay. In the figure above, name the tangent line. So the tangent line here is this line here. It's AB, line AB. Okay. Name the point of tangency. That's the point where it touches, and that's point A. It says name a tangent ray. Remember that a ray can do that like that. And we always start with the end point. A is the end point. It goes on to B. Even if we had a point here, like let's say C, remember we'd call that ray AC. Okay, and then how about a tangent segment? Remember, a segment's just a line with endpoints, so segment AB would be a tangent segment, or we could call it segment CB. Would be a tangent segment, even though the point of tangency is A. Okay, so going from there, let's talk about what's special about tangent lines. Okay, so hopefully we can identify them. Let's talk about what's special about it. If a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. Perpendicular. Okay? And so in the figure above, the radius to the point of tangency, that's AO, okay, forms a right angle with the tangent line. And therefore, we know that the measure of angle BAO, since it forms a right angle with the point of tangency, is 90 degrees. Okay, so now we're going to use that to solve some problems, finding angle measures and side lengths. So in our first example, we're given that that ML and MN are tangent to circle O. So since these two lines are tangent, and I want us to find X, we know that the radius drawn to the point of tangency, which these radii are perpendicular. Makes a perpendicular angle. So we have 90, 90, 117 here, and we need to find X. So this figure OLMN is a quadrilateral. Quadrilaterals have 360 degrees, some interior. So 360 minus 180, that's the 90 plus 90, minus 117. So that gives us 63. So X is 63 degrees. And that's from us knowing that these tangent lines then create perpendicular 90-degree angles with the radii drawn to them. Okay, in the second example, we want to find the area of the circle. And in order to find the area of the circle, we need to know the radius. Now we have radii drawn here and here, but and so we can try to use what we know about radii or about tangent lines to figure this out. Okay, here we have the 17. 17's for the whole hypotenuse. And we'll say, okay, since this is a tangent line, AB is a tangent line to the circle, we know that the radius drawn to it creates a 90-degree angle. So now this is the right triangle that we can use Pythagorean theorem to solve. So x squared plus 15 squared equals 17 squared. So x squared plus 225 equals 289. That's 17 squared. Subtract 225 from both sides, and x squared equals 2, nope, not 2 anything, equals 64. Okay? So if x squared equals 64, then that means x equals 8. That's our radius. Our radius is 8. And so that's what we need in order to find the area of a circle. That's pi r squared. And so we'll say area equals, our radius is 8, 8 squared pi, or 64 pi. That's in terms of pi. If we wanted to do that in other terms, we could plug 64 pi into our calculator. We get 2.01.1. Okay. All right, flipping to the back. Okay, top question on the back says, does this figure show a tangent line? Explain. All right, so now we have to think about this a little bit. How do we know if this shows a tangent line? We don't have anything about angles. That would be one way. Remember, we know that tangent lines are perpendicular to the radius drawn to the point of tangency. But we do see a triangle. If this is tangent, then this will be a right triangle. And so we can test this out by using Pythagorean theorem. If Pythagorean theorem works, then we know that it's a right triangle. 15 squared, 16 squared. So does this work? 25 plus 225 equals, what's 16 squared? 196? Pretty short. Nope, can't be 196. That doesn't even make sense. 16 squared is 256. There we go. That makes sense. 256. Okay? So 25 plus 225 is 250. Does 250 equal 256? No. So are the lines tangent? No. The explanation is triangle with sides 5, 15, and 16 is an obtuse triangle, not a right triangle. Okay. Tangents will create a 90-degree angle in a, like as they are in right triangles. There we go. All right, so there's my explanation. Okay. Next problem, it says find the value of x in the circle below. Now, this is a little bit different than the first time we've done this on the front of the other page. Notice the first time we were given the whole hypotenuse. Okay, and this time we're not given the whole hypotenuse. We're given the exterior part is 7, and then this interior part is x. So we're going to set this up just a little bit differently. Again, we're assuming that this is a tangent line, and so our radius drawn to that point of tangency will create a right angle. And so now we can set it up as x squared plus 10 squared equals this side squared. Now we're going to rewrite this side as just kind of one entity as x plus 7. Okay, so x plus 7 squared. So x squared plus 100 and x plus 7 squared. I'm just going to show work up here a little bit. In FOIL, x times x is x squared, x times 7 is 7x, 7 times x is 7x, 7 times 7 is 49. So equals x squared plus 14x plus 49. And from there now we're going to just be solving for x. So I'll subtract x squared from both sides. It's gone. I'll subtract 49 from both sides. That gives me 51. So 14x equals 51. Divide both sides by 14. And what will that be? 51 divided by 14 is a decimal. I wonder if it goes into a nice fraction. Nope, it doesn't. 51 over 49 is as simplified as it, or 51 over 14 is as simplified as it gets. So 51 over 14, or as a decimal, 3.64, we'll say. Okay, so either one of those. So just making sure that you recall foiling or box method, however you learn to multiply binomials by binomials. All right, the second theorem that we can deal with tangents is that two segments tangent to a circle from a point outside of the circle are congruent. Okay, in the figure above, notice that point E is outside the circle. It's here. Okay, EC and ED are tangent to circle A. And therefore, we can conclude that EC is congruent to ED. We know that these two segments are congruent. Okay? And so we're going to use that for this next problem. We have the perimeter. Actually, let me show you why that is really quickly. Okay, so if I draw this in, this AEN, and we deal with these two triangles, ignoring these marks for right now, we know that these two are the same because they're both radii, right? We know that these two are the same because they're both 90-degree angles, and we know that this side is the same because it's a shared side. Okay. And so what we have here is the HL theorem. Okay, hypotenuse leg. It's a right triangle because it's tangent from the radius, a radius drawn to the point of tangency, 90 degrees. The radii are the same, so that's their leg, and the hypotenuse is the shared side. So the HL theorem is what helps us to see that that's the same. Okay, so again, showing you that because I want you to know that geometry isn't magic. There's a reason for these theorems and for being able to use these facts. Okay, so from there then, let's use that. It asks us to find the perimeter of triangle ABC given that circle O, sorry, that's not a zero. Circle O is inscribed in triangle ABC. So inscribed means that the circle is tangent to the triangle in 3 places. Okay, because it's inscribed, we know that point E is a point of tangency, point F is a point of tangency, point D is a point of tangency. Since it's the point of tangency and we see these exterior points drawn to the point of tangency, I know that AD is congruent to AF. I know that DB is congruent to BE. I also know that FC is congruent to EC. So I can fill in these missing sides, 10, 15, 8. All right, and then I can add these up. 16 plus 30 is 46 plus 20 is 66. And so that's our missing side. Or not our missing side, our perimeter. All right, so those are the theorems involving tangency and points of tangency and how we can apply them to find missing side lengths and angle measures. All right.